All right, so I'm Adam Milker. I am an FFmpeg developer. I've done a lot of work on audio codecs and video codecs. I was crazy enough to write a DALI decoder a year ago, and I wrote the first non-libopus based encoder and I released it just like a week ago. So what I'm going to be talking about today is AV1. Now, for those of you who don't know what AV1 is, I've prepared a slide for that. So AV1 is supposed to be interoperable and open. So it's always going to be royalty free, and it's going to be optimized for the internet, so that many of the people who are in this room can directly benefit from that. The increase in video compression, the royalty free, and all the other stuff. It's going to be scalable to any modern device at any bandwidth, mostly. It's going to be optimized for the hardware, so that you can easily decode that with little power on a hardware decoder, and as well encode it with varying degrees of success, and all the other stuff which you see all the time in marketing. This, by the way, I stole from the AOM website, so I would never write something like that. So decode it, this would mean something like that. These are the real bullet points. So it's going to be royalty free. It's going to be it is already in development, and it's already open. And lots of companies are participating in the development of this codec. So all of the major players like Amazon, Netflix, Google, YouTube, Mozilla, and so on. And so whatever happens, the codec will see adoption. But so what's important now is to get the codec to be competitive with other codecs that are being developed right now, and also make it an upgrade to any codecs which are currently being used. So now, unfortunately, not all companies have joined. So there is still some intellectual property out there which we cannot use. So that means that we have to get clever, and we have to go around that in some ways. And the whole process of going around means rediscovering new ways of doing something which might or might not be more efficient. So moving on. The reference encoder is based on VP9 without VP8 support, but with bug fixes. So some of those big bug fixes were meant to go into VP9, but didn't. So they made it into VP10, but VP10 got turned into AV1, and so we carry on. So the way that the development works is companies contribute experiments, and these experiments make it into Git master of the encoder. And after being integrated, the experiments are supposed to go through intellectual property review. So there's a team of lawyers who looks at the description of the encoding tool and tries to find patents which have been updated or which haven't been updated, which match the description of what the tool does. So, and eventually, after the bitstream has been frozen, which should happen around Q4 of this year, all the experiments should be removed. This is what's, in my imagination, what's meant to happen, but it hasn't happened yet. So about the experiments, there are currently 50 experiments, and granted, some of them might don't sound appealing or don't sound like they contribute anything, like emulated hardware or debug bitstream. But the point is that most of these experiments increase encoding efficiency, and well, there's just 50 of them, and they're being constantly developed and updated. So there's a whole lot of development going on right now. So I cannot really cover every single of the 50 tools of the experiments which are currently in the codec. Not to mention that every month new experiments get added, and some experiments get enabled by default, and so it's kind of difficult to keep track of. But I'll just go through some of the coding tools which have been demonstrated to give gains and have are good candidates for being, part of the codec and the specifications later on. So the first tool which I'll cover is directional deringing. Now, directional deringing was something which was ported from Dala, and it was required in Dala because Dala used overlap, and most of the encoding techniques in Dala contributed to some degree of ringing in the image. So this deringing filter was developed for Dala, but it turns out that since it's right at the very end of the encoding process, at the decoding process, you can just easily paste that into any codec and it will just work. So the way it works is you first segment the image into 8x8 blocks, and then you scan for a direction inside this 8x8 block. So you do that by computing the least squares method, I think. So the direction doesn't really matter. What matters is that it does a conditional replacement filter. So instead of blurring out any artifacts and by extension any detail in the image, it only acts on very obvious ringing patterns. So in case a single pixel deviates by some amount, which varies as a function of how far away you're perpendicular from the direction vector, it will replace it with some kind of an average. So it works really well, and it gives, I think, around 2 or 3% improvements. It's also easily simulable, and it has currently been enabled by default in AV1. So this tool is probably going to make it into the final version of the codec. Another tool is PVQ. Now, PVQ is going to give by far the most gains, but it's by far the most difficult tool to integrate. And what you can think of PVQ is, you can think of it as a black box where you can insert any kind of coefficients in the frequency domain, and PVQ will predict from both the current image and whatever you give it in to predict from. So it can be previous pixel values, previous coefficient values, or it can be, for instance, coefficients from Luma, and you want to predict chroma. So the way it works is, well, I'm not really going to explain it, but you can see from the diagram that if you imagine the coefficients inside a block as a vector, you can describe that vector as pointing to the surface of a sphere, of an n-dimensional sphere. And if you have another vector, which is what you're wanting to predict from, you can do just a Hauss order reflection, and then you just send a theta angle, which is n-1 values long. So I just wanted to spend some time on discussing PVQ search, because I think PVQ search is it's an important problem which also needs to be solved and made faster. We currently have an implementation which is carried on from Opus, because Opus used a PVQ search as well. We do RDO on the PVQ search, so that's a bit different, but the root of the problem is very simple. So if you have a vector and you want to quantize it using a PVQ search, you just normalize the vector to an L2, which is the Euclidean norm, which is basically you sum up the squares of each component, then you do a square root, and then you divide each component of the vector by the square root, and well, you do that for the output vector quantized as well. So it's a simple problem, but it gives great results, and I think it's the way to do vector quantization. So if some of you wants to go ahead and give it a go and give it a try and improving it, you will improve performance not just in Dala, not just in Opus, but in AV1 as well. So that will be useful. The properties of PVQ is also what makes it very interesting. Using PVQ, we can vary the codebook, so we can optimize it, for instance, for areas which have low contrast. So this is what activity masking tries to do. It attempts to provide better resolution in low contrast images. And this is in contrast with HEVC, which attempts to aggressively remove details from the original image. And if any of you has done any encoding using HEVC, they will know that SAO basically is a tool which you turn off if you see any bad results immediately. So activity masking is something which is difficult to kind of make it into AV1, since it requires a different distortion function, but we're all actively working on trying to make it into something usable in AV1. So another tool which is also ported from Dala is Chroma from Luma, and since we do PVQ entirely in the frequency domain, this means that we can also inject the values from Luma coefficients, and more accurately describe what exactly are the details in the chroma. So you might ask, well, how does it work when you have a subsampled chroma? Well, we use TF switching to throw away any details. Remember, this is all in the frequency domain, so you cannot do rescaling and conversion in the spatial domain, since we're all in the frequency domain. So the resulting coefficients will be used in a DCT transform, and that's one of the difficulties in implementing Chroma from Luma in AV1, since AV1 has currently two different transforms. AV1 has DCTs, which are the standard way of doing transforms, and there is an ADST which allows you to in some circumstances get better results, but there are more transforms being planned to be added into AV1. So Chroma from Luma is kind of a difficult thing to implement, but the results really show that there's a big improvement in chroma detail and in Luma detail as well, since in order to better describe chroma, you need better Luma. So that's why CFL is looking like a nice feature to implement into the final version of the codec. Now, a note is that it works for 444 and it works for 420 formats, but it doesn't work for 422. So if you want to use 422, please don't just use 444 or 420 or just increase the bitrate. You can always just increase the bitrate like the old 80 megabits MPEG-2 streams and pad the bit stream. But in order to pad the bit stream, there's a convenient segue here. You need to ensure that the codec, that the rate control system will not overshoot. So it will not overshoot grossly, since if you plan to pad, then you obviously want to pad to some bitrate, but you don't want to overshoot, of course. So this is what I'm currently working on. I'm trying to fix the rate control system in AV1 by just scrapping it and by inserting the rate control system from Dala, which was also the rate control system from Tioro, but was ported to Dala. So the rate control system, which I'm working on, tries to basically predict the amount of bits that the current frame will use, and it does that by just this simple model, and the scale value is what's modified from frame to frame. So the codec will first use the scale value from the previous frame, and will predict the bits the current frame will take, and will then after the frame's being encoded, it will measure the real scale value, since you know how many bits you've used and you know the quantizer, and alpha is just some an exponentiate value which is different for all frame types. And it will correctly and it will try to smoothly transition scale from one frame to the other frame using a second order Bessel filter, which will also throw away any extremes in the final quantization values being used, and as such it will give a smoother visual experience of encoding. So it won't do any gross overshoots that the current rate control system does. And just to share something with you, I have seen on YouTube a 200 megabits sustained for 5 or so seconds, on a stream directly from YouTube. Granted, it was VP9, but it was 4K at 30 frames. But still, nothing warrants 200 megabits of continuous usage for a few seconds. So, and this rate control system also will support a way of easily providing chunks to kind of encode. So instead of encoding separate 10 frame chunks, a few seconds worth of video, of chunks, you can just signal a reset in the 2-pass mode of the rate control system, and it will reset all the statistics, and you can just continue on encoding as if you've just started encoding a new frame. And all right. And another feature which I'd also like to talk about shortly is RANS, and RANS is being developed by Google currently. And RANS will offer big improvements in the coding speed, but unfortunately there are some drawbacks. It needs a big enough buffer to store all the symbols in the encoder before reversing them and writing that as a bitstream, because it works kind of as a stack. So there are some hardware manufacturers which aren't content with having a huge buffer, but at the end, it's either this or the Dala entropy coding system, both of which have the same efficiency, but RNS has the advantage of having a higher decoding speed. And there are also some experiments which I cannot really dedicate the entire time to talk about, but there's EXT-ETX, which will give more transforms, which as I already mentioned, will kind of be a bit of a problem for CFL, but I'm sure we can make do with it somehow. There's also an adaptive coding order, so the old zigzag, which isn't patented anymore. It turns out that the old zigzag may not result in the best encoding efficiency. So if you have some kind of other patterns you can use, and you can do RDO to figure out which pattern is the best, then yeah, if the experiment turns out to give improvements, we'll also make it in. And also there's 64 by 64 transforms, which aren't quite certain that will make it in, but will provide big gains on any kind of large uniform images. So with that, I'd like to end the presentation, and if there are any questions, I'd be happy to answer them.
We have time for 3 or 4 questions.
All right.
Will you support interlaced?
Yeah, that's the $1 million question. And so the question was, are we going to support interlaced? And well, I'm not sure.
You say no.
No comment.
Say no. Just say no.
I cannot say no. I mean, you know how it is. It's not designed by committee, but it is still designed by some people with various interests. So whether it will not make it or make it, I cannot say, but many of us have strong opinions about it not making it.
How strong?
Very strong. Yeah, so yeah, well, the question was, wasn't the bitstream going to be frozen in March of this year? And well, the bitstream was going to be frozen last year, and it was going to be frozen many times before that. But you know how it is. You just have to keep extending, because some features you really don't. You need some more research to improve some features. But what's important is that we don't want to delay it too much, because by that time H.266 will be out, and we'll have to compete with that, and we want to get adapted before that, so that less people will adopt the less royalty-free equivalents of video compression codecs. So anyone else? Yeah.
Well, so this is some pretty amazing work. And my question was, is from the outside, it looks like you either follow the footsteps of AV1 and the family, or be like foreign work. And I've seen some work, research work on motion prediction that is stored as a 3D scene.
Yeah.
Is it?
Well, you should look into yeah. So the question was, have we looked into storing motion information as a kind of a 3D type of thing, where the third dimension is time, I presume, right? Well, there was an experiment that Ziff tried to make. It was a codec. I don't remember its name, but it used wavelets in 3 dimensions to try to compress video, and as far as I remember, you could actually see, information, images ahead of time, before they happen, as kind of a ghostly, images. But apart from that, nothing's been looked into it, because it's just so radically different and sounds and is difficult to kind of do enough research to get something which is actually implementable and it gives encoding gains and doesn't require much hardware to actually implement. So I don't think that it's the way to do it, and I don't think it's the way to do it for the next 50 years or something. All right, there's a person there in the back.
I have a question which is not really codec related, but MOOCs related.
Okay.
Are you going to work on having it in MP4 right from the start? Because that would simplify deployment very much.
So the question was, are we going to work on MP4 encapsulation, right?
Yeah.
Well, let's first get a codec which is presentable, and then we'll work on MP4, muxing, because as it is right now, all of us are working on improving the codec, but I'm not sure why you want to use MP4, because MP4 is what, 20 years old now? If it ain't broke, yeah, but.
Just about another obfuscate where most people can't use it because it's not used before.
Well, regardless of whether it's in MP4, it will mostly be used on the internet, and right now WebM is the de facto standard for video and audio encoding on the internet, so it will first be implemented in WebM. So, well, sorry about that. Any other? Yeah.
This is maybe more of an implementation thing.
Yeah.
Maybe some of the new experiments precluded. Will there be? Is there plans for non-tile multi-threading?
So the question is, are there plans for non-tile multi-threading?
Or the experiments might, make threading really feasible?
Well, there will always be frame threading, but there will always be well, in the decoder, but there will always be tau threading as well. So right now there are no plans to drop tau threading decoding, but I think there were some plans to drop frame parallel decoding. So there's that. You have to ask Thomas Didi on IRC. All right.
We have time for, I think, one more.
All right, one more question. Someone.
Someone was first.
All right. Yeah.
You have to play when you decide what feature to set in the codec about hardware encoding. Like on a Raspberry Pi, you can encode some formats, put the hardware, etc.
Right. So the question is, how do you decide which feature, which coding tool is implementable in hardware, and which one to actually implement into the codec? And the answer is that during initial review, you'll get some feedback on whether the tool you're trying to encode is feasible. And finally, after IP review or around that time, after it's in Gitmaster, the hardware companies, which are part of the alliance, will go over the coding tool and will try to see if it's implementable using current hardware decoding production means, and if they give it a go, then they give it a go and it goes in.
Okay, last question.
All right, last question.
How is the compression ratio?
How is the compression ratio? Well, right now we're doing quite a lot better than H.264. We're doing better than H.265 on basically all metrics. And after the encoding tools, which I've mentioned, are implemented, we'll do slightly worse, maybe PSNR based, but PSNR is a horrible metric, so so perceptually we will look, you know, quite a lot better than anything which is currently out there. All right, well, that's it. So thank you for having me, I guess.